So we are going to start chapter 5, and we'll see how far we get. And then this is the last chapter that is our content for our test that is a week from today. So September 8th is our first exam on chapters 2, 4, and 5. I am going to be spending some of class time next week on how to study and also giving you some problems to work. So this is the last of our content. We'll see how far I get. I've been talking all day. Okay. So, we've talked about our NIST standard, which is a standard we can purchase, and we know it's correct, and we can compare our values to it. There's also other ways to do standards, and you've done some of this already. We're just putting some new language to it. So when we have analytical standards, we can have a primary standard and this is a reagent, so a chemical, with an accurately known amount of analyte. So this can be a NIST standard. This can be, you can buy it just if you look on your chemical bottle, it would say purity, grade, and for it to be a primary standard, it needs to be 99.9% or higher pure. So a lot of the chemicals you work with in analytical and gen chem and organic are about 95% pure. That's like how we buy them from the chemical company. It costs more money to get a 99.9% pure substance because they have to do extra purification processes. So that's when you can use, those are two examples of a primary standard. The concentration of a secondary standard needs to be first determined. So this is, you need to do an experiment to actually determine what it is relative to a primary standard. So a good example of this is when we start to do titrations. So our solutions that are acids or bases, we make them, our like concentrated acid is in a jug, it's a liquid, and then we make our solution to be 1 molar. But that jug of liquid is actually not 99.9% pure, so we have about a 1 molar solution. Up to before you took analytical, that about a 1 molar solution, that was good enough. It did its job. Now that you're in analytical, we need to know exactly what that concentration is. So we need to know it's 1.005, or that you completely messed it up and it's 0.9562, which is fine as long as you know it's 0.9562 and not 1. So it's fine if it's off, you just need to actually know what it is. So that's what we're going to be doing in lab when we start doing titrations, is our primary standard and our secondary standard. What we'll also do in lab is standard curves. So we're going to talk about 2 in this class. First one is an external standard. Hold on, I'm like choking on myself. This is the most common method. Of standardization, and you've all done this. So in Gen Chem lab, if you took Gen Chem here, I guess I should say, I know you've done this. What this is this is using a calibration curve where the response of an analytical method is measured. Is measured to a known concentration or a known quantity. These curves, if you're a biochemist, you'll hear Dr. Lane and Dr. Kennedy call these normal curves. or you might, in general chemistry, you probably call them calibration curves. And an analytical chemist would actually call it an external standard curve. They all mean the same thing. So what we have is we have known quantities of analytes, and these are our standard solutions. So a standard contains a known concentration of analyte. And then we put that into some sort of instrument and measure the response of it. We also run a blank, and this is a solution that does not contain the analyte. But the solvent is the same. So if you were just making solutions in DI water, your blank is just going to be DI water. When you get to some more complicated analyses, your blank is not going to be just DI water. It will be whatever your solvent is. And then your corrected value is your standard minus your blank measurement. And this is what you plot as your Y value. So if we look at this standard curve, this is our Y value. This is our X value. So our Y axis and our X axis. So on our Y value is we have our corrected value, so we're measuring absorbance. Absorbance actually is unitless, so this is an arbitrary unit. So this is the one time that when you report a number, it does not have to have a unit. And then our X-axis is our concentration in micromolar. So here we have a calibration curve for a specific protein in blood. A blank was run and gave us a 0.3 absorbance. And then the sample of blood was run and given 1.4, find the concentration. So what absorbance unit did you get for the actual blood sample? What, just absorbance?
Yep.
No.
Okay.
All right. My confidence is down.
So we got 1.4 for the blood, and we have to always subtract our blank. So what that means is that even when the sample was not in the solution, whatever that solvent was still gave an absorbance value of 1.3, I'm sorry, of 0.3. So the real absorbance of the protein in the blood is 1.1.
Is that us using the corrected value?
Correct. Correct. That's the corrected value. Then over here we have our curve. So now we know our absorbance is 1.1. What is our concentration? And I didn't give you an equation, but we can just interpolate. And what do you get for your concentration?
Maybe 11, maybe 12. That's it.
And all of those answers are correct, because if you look at our scale, we know it's between 1 and 2, and then kind of any number you choose after. What unit are we in?
Micromolar.
Perfect. So there's 12 micromolar or 11 micromolar of protein in our blood. So let's do another one. So here we have a calibration curve measured for different concentrations of copper. So I have copper is actually a pretty chemical metal. It absorbs color. So you can see the more copper we have, the deeper blue color we have. The equation for the line is y equals whatever this is. What is the concentration of copper in a sample whose absorbance is 0.198?
Would the absorbance be the X value?
So let's look at our axes. So what is our unit on the x-axis?
Concentration.
Polarity.
Concentration. Molarity.
Concentration. And our y-axis is our S.
Standard deviation.
The way I also remember this is like a Y is like taller than an X. So it's hard like tall axis. I don't know. So Y and X. So to answer that question, what are we plugging this in for? Are we plugging 0.198 in for X or for Y?
Y.
We're plugging it in for Y.
Wait, why?
Because our signal is on the Y axis.
Why?
Y. And shout it out when you get it.
6.68 times 10 to the negative 2 molar. Or 0.
10 to the negative 3.
6.64 times 10 to the negative 3.
That second. Whoever said that.
Well, hang on.
I mean, I know, what's an order of magnitude between fractions?
Yeah, come on.
So we got this to 10 to the negative 3. And you could also just write that as 6.64 millimolar to get rid of your exponents.
Would we use 2 suffix?
Um,
Or would we use
yep,
2?
so we have 4 and then we have 2. So it's just 6.6 millimolar. Good catch. So hopefully that feels familiar. We've done that one before. Now I'm gonna blow your mind, and now we're gonna talk about one that you haven't seen before. So this is standard additions. So if you remember what we just talked about, those are called external standards or normal standard curves. This is now a standard addition. So now this is a calibration curve that you use to determine the relationship between signal and concentration. So it's just what we did on the previous one. Except we use this when a calibration curve cannot be conducted due to matrix effects. So if you go into lab and you need to decide what method to use, if you have matrix effects, you need to use a standard addition. You might be wondering, what is a matrix in terms of this class? I'm sure we have matrices and everything. So matrix is everything in a sample other than the analyte. So for example, if you're trying to measure the caffeine in soda, what are some of the other things in soda? Sugar. Wow. Salt. Like dyes. Basically there's like a lot of stuff. So all of that is the matrix. So everything but your caffeine is the matrix. And I would call that a complex matrix. So there's a lot going on there. So if I asked you, please measure the caffeine in this Coca-Cola, you should think I need to do a standard addition calibration curve, because if my just to make my standard as caffeine and water, that actually looks nothing like Coca-Cola. So a standard addition, how do we account for that matrix? Where are we going? There we go. So how do we account for that matrix? We take a known amount of analyte added to unknown sample. And then that is going to give an increase in the signal. So then from the increase in signal, the original amount can be determined.
Amount of what?
Amount of the unknown, sorry.
Yeah.
UK, unknown.
Like,
Yeah, sorry, unknown. So this sounds complicated, but this is not as complicated as you think. Imagine for some reason you really want to know how much I weigh, but I don't want to tell you. And also for some reason we're at a vet's office where there's like a big scale that we can step on together. Emma knows how much she weighs, so if we happen to walk over the scale at the same time, she just subtracts what she weighs, and now she knows what Dr. S weighs. Does that make sense? Because I can come up with another one. So I think it sounds fancier, but if we have an unknown amount of sample, so we don't know the concentration, we don't know how much Dr. S weighs, what I'm going to do is I'm going to add a weight I know. Emma knows her weight, so she's going to add it to my balance. And now we can figure out the unknown. Feeling good about that? So if we go back to solutions, so if we have our soda, and we're trying to figure out, so soda with UK, unknown, caffeine, I'm now going to add to it caffeine standard. And when you hear the word standard, that means we know what the concentration of that is. So caffeine standard means we know that concentration. So you can do a single standard addition, which is where like Emma would just stand on my balance with me. Or you could do a multi-point, which is where everyone then takes a turn to stand on the balance, and then we can kind of collectively figure out what Dr. S weighs. So in our lab, we're always going to do a multi-point standard addition. So that means there's going to be multiple solutions, so a series of samples. That contain the same volume of unknown. That's fairly important. And increasing volumes of our standard. So as our example to the right, all of those flasks, those purple flasks on the screen, contain 25 milliliters of an unknown manganese 2+ solution. Then 0 to 5 milliliters of a standard 100 ppm manganese standard is added. So let's think about that. So we have 6 volumetric flasks up here. Dr. S gives you an unknown manganese solution and says, what is the concentration of the solution? So you take 25 mils of it and you put it into every single flask. So your unknown is in every single flask. Then you add your standard, 0 to 5. So that first one does not have any standard in it. The second one has 1 mil, 2 mils, 3 mils, 4 mils, 5 mils of our standard. And if you look down at our x-axis, interestingly, our x-axis is in volume of standard, so it's not in concentration. So we have 0, 1, 2, 3, 4, 5 on the x-axis too. Why is my solution that has no standard in it already purple? Right, because it has the manganese in it. We just don't know how much. So the unknown is in all of these. So you go into lab, you make your solutions, you measure this is a just instrument signal, most likely absorbance, since these are pretty in purple. And we got a nice linear equation because the more you add the standard, you're adding it in incremental amounts, your line is just going to increase. But there was already standard in that first one, so notice it does not cross through the origin. There's already manganese in that first one, so there is an absorbance value. So what we do, and sorry that I ran out of room, is your x-intercept equals the concentration of your unknown with a little f after it, and that means in your final, like your final diluted solution. So when you solve for the x-intercept, your x is always going to cross at a negative value, always, because you already have your unknown at your 0. So it's always going to be negative, but there's no such thing as a negative concentration. So we just take the absolute value of it. That equals the concentration of the manganese in this solution. So in whatever volume that solution is. So if I ask you for what the concentration of solution was in this original unknown, you have to do an M1V1 because you took 25 mils of it and diluted it to this volume. And now you know the concentration of this volume, so you have to do an M1V1 to get back to the original. So that's what that little F means. It means that the final diluted solution. So you're figuring out the concentration of this diluted solution. So if I just show you a curve, an X versus Y curve, Y versus X curve, how can you tell the difference between a calibration curve and a standard addition curve? There's a few ways.
Units.
The units, so your x-axis units. So what are they in a standard calibration curve?
They were concentration.
They'll be your concentration. What are they in your standard addition curve?
Milliliters volume.
Milliliters or volume. How else?
The intercept?
Where it's in the intercept is.
The origin.
In a standard curve, when you have 0 concentration of your analyte, you should also have 0 instrument signal if you've done your experiment right. So it should go through the origin. Your line should go through the origin. Whereas when x is 0 in a standard addition, it's a positive number. Okay. Do you feel like you could differentiate between those two curves? Let's add some math then. So this is a type of problem you might see. So I'll give you a minute to read it. And the first question I'm going to ask you is this an external calibration curve or a standard addition? So calibration curve or standard addition?
Standard addition.
It's a standard addition. So it holds 1 mil of the unknown solution. Every solution holds 1 mil. And then we have increasing volumes. So all of those are giving us hints that this is a standard addition. So the first thing you need to do, solve for your x-intercept. Make that a positive number, just take the absolute value of it. And then account for your dilution, because it's asking for it in the original sample. So how do we find our x-intercept? Y equals to 0. And then you should get a negative number. And if you got that number, then write m1b1 equals m2b2 and account for your dilution. So what's our M1? What's our first concentration? Just from the problems. Or I guess that can be your M2 if you want it to be. But what concentration is given to us? 1560 parts per billion. What volume of that do I have? And remember up here, x-intercept equals our x final diluted volume. So that's where your 8.526 times 10 to the negative 4 milliliters goes. We're solving for the concentration and how much of the original sample is in our solution. The original unknown sample. 1 milliliter. So what do you get for M2? 1.33. It was said in synchrony. I enjoyed that. We'll get there. So some things to look out for here. If a problem says series of solutions, final volume, original, you are going to have to do an M1V1 equals an M2V2 at some point in that problem. Because that means a dilution happened. And then also, when you're doing an M1V1, make sure your units are the same on both sides. That's another tricky. Okay. Questions on that? So that was an external standard and a standard edition with examples. And then for some reason the book has this after, but we're going to talk about linear regressions at the very end. Real fast, there is a third calibration method called internal standard. And we are not going to cover that in this class. If you get to instrumentation, you'll definitely cover it. But if someone says the word internal standard, I don't want you to just look at them like you have no idea what they're talking about. It's just another method. So now let's talk about that y equals mx plus b that we kept seeing in our calibration curves. That's called the linear regression. So that's the best straight line through your data points. And what you end up getting is y equals mx plus b. M is your slope, b is your y-intercept. So if you have two sets of data, just looking at that, the data on the left and the data on the right, which one of those has a better linear regression? The right. So when we fit these, we get a linear regression. So we get a line that tells us how those are related. But this one has a higher precision. So you're going to have less uncertainty if this is what your data looks like. Versus if this is what your data looks like, you're going to have a high amount of uncertainty. So the goal of linear regression is to determine the best estimates for your slope and your intercept. The difference, how far this point is away from your regression, is the result of indeterminate errors. And we can calculate that error, and it's through Excel. So what this UX is our absolute uncertainty. So this is putting a number to the uncertainty. This is what we are going to be doing in lab on Tuesday. So we're going to use Excel to calculate the uncertainty using this equation. So this table is going to be helpful for lab next week, so make sure to bring your course packets. But that's what we'll do on Tuesday. Experiment 2. So with that, we finished. So that is all the content on your exam next Friday. So we're going to go over how to study next week, and then I'll give you some problems, a review sheet to work on Wednesday, and then exam on Friday.
Is the next homework for chapter 5 Wednesday or something?
Thank you for saying that. Our next homework is due Wednesday, so before the exam. And it's on this chapter that we just talked about today. So you can start it and finish it this weekend if you want.
No quiz with that one.
There is no quiz next week, so just the exam on Friday.